Hello, I am Salakan, and this talk is about co-contextual typing inference for the linear pi calculus in Agda. This is joint work with my supervisor Agda from the University of Glasgow. Let's first have a brief recap and see what typing inference actually means. And we'll start by looking at type checking, where we are given the expression or the process and everything we need to check whether the expression or process is well typed or not. So this includes the typing context, in the case of expressions, the types of the expressions, and for both expressions and processes, we also need to know about the types of all the bindings that occur within them. We give all of this to the type checking algorithm, which will tell us whether the expression or process is well typed, maybe give us a derivation as a proof showing it is well typed, or it is not and give us a derivation, a proof showing that it cannot possibly be well typed. When we do type inference, we are given the expression and the typing context, and it is up to us to deduce what the type of the expression is. This has no equivalent notion in the process world because processes are untyped. When we do typing inference, we not just deduce the type of expressions, we also deduce their typing context, which also applies to processes. So here we push the expression or process down and we get out of the algorithm all the minimal requirements we need so that an expression or process is well typed. Most importantly, when we do typing inference, we deduce what the types of the bindings occurring within the process or expression are. Now that that's out of the way, let's have a look at the pi calculus. As many of you probably know, the pi calculus is a language for concurrent communication, where we have processes that we can execute in parallel. And these processes communicate with one another over communication channels that they share. They send messages over these communication channels, and these messages can include channels themselves. This is called channel mobility. In our case, we have a small expression language embedded within the values in our process language, and this expression language is in charge of basically introducing and eliminating products and sums. So this is our expression language, where we can refer to a variable. This is, for example, a channel or something that we received on a channel. We have units, we have pairs, we can project those pairs, and we can construct elements of the sum type. Now let's have a look at processes. These processes are indexed by the number of free variables that occur within them, and we use the Bruin indices to refer to particular variables. We have several constructors. We can end a process, so this is a terminated process that sits there and does nothing. We can introduce a new channel that is then available in the continuation process. This is why we do +1. We can replicate a process, run infinitely many copies of it. We can receive something on a channel, and when we do that, we have to point to the channel that we're receiving on. This is an expression. And then we have to give the continuation process, which will have whatever we received on that channel available as a variable. We can send over a channel, and for this we have to specify both the channel that we are sending over and the thing that we are sending over that channel, and then we give the continuation process. We can compose two processes in parallel. This will allow them to communicate with one another. And we can do a case match where we have to first give the expression that we are matching on, and depending on the outcome of that, whether it's left or right, we will continue with the continuation process on the left or on the right, and both of those continuation processes will have the element that we case split on available in their context. Okay, let's now have a look at the types. These are types for the shared pi calculus. that is a bicalculus where you cannot restrict how many times a channel is meant to be used. Our types are going to contain metavariables, holes within the types, because we're doing typing inference, so we need some way of denoting the case for where we don't know yet what the type is. Types will be indexed by the number of metavariables they can refer to within them. So this is a Debrun-like syntax, but since we don't have any introduction rules for new bindings, we just stay on the same number of metavariables. So we have metavariables, we have channels for which you have to specify the type of the payload, we have unit types, and then products and sums. And we use the notation below, the triangle to the left, for substitution. This means that we are substituting in a type T the holes within T as per sigma. So sigma will have a map from holes to types. Okay, now that we know what typing inference means and what our base calculus is, let's have a look at what we are about to do, which is typing inference co-contextually. So we will traverse our syntax of processes and expressions bottom up, and we will collect requirements. Whenever we have a split in the tree of syntax, we will merge those requirements pointwise in the context. And this allows this algorithm to be easily parallelizable because you don't have any dependencies between the different branches of the tree. When we look at the types of our inference algorithms, they will look something like this, where we are given a process with n free variables within. And maybe if we succeed, if we think that the process can be well typed, we will return for a number of metavariables, we will return a context with one type for each free variable within the process, and those types will have many metavariables within. Similar for expressions, only that we also return an extra type for the type of the expression. And down below, there's a couple of simple cases where, for example, for the terminated process, we just return a fresh context of types, each type being a metavariable. And whenever we have to merge requirements, we run the inference independently on both branches. And once we have the answer, then we merge them into one. As we said, we traverse the expressions bottom up, collecting constraints. What are these constraints actually like? In this case, these constraints are equality constraints, where we want to make sure that both sides of a constraint can be solved into one same thing. And this means that we will need to find a substitution from metavariables to types, such that when we apply that substitution to both sides, we will equalize them both. This is solved by first order unification, and whenever you create one of these constraints, you can immediately solve it into substitutions and apply those substitutions to the typing context. So therefore, you don't need to keep these constraints, you don't need to push up these constraints through the inference algorithm, you can just handle context. Okay, let's now go over what we just did and slightly change things to introduce linearity into our type system. We will introduce usage annotations that will tell us how often we are meant to use something, and these usage annotations are going to be 0, 1, or omega. 0 meaning you cannot use something, 1 meaning you have to use it exactly once, and omega meaning you may use it as much as you like. As before, we will have metavariables in the types. In this case, we will have metavariables both within usage annotations and within types. we want to keep them in one single place together, both kinds of meta variables. So we will have what we call a kind and context, where we will say for each of the meta variable whether that meta variable is meant to be used as a usage annotation or as a type. The only other change is that we now introduce usage annotations in channels. So for each channel we will say what its input usage annotation is and what its output usage annotation is. Then we will have to modify substitution as well to make sure that it is kind preserving. Another thing that we will have to define is how to split up resources on branches in the syntax. So we will say that 0, the usage annotation 0 is the identity on both sides, and that you can always go escape into omega, whatever the usage annotations you're adding are. When we split a channel, we split both its input and its output usage annotation, but we leave the type of the payload unchanged, so we preserve that. And then we define a type as unrestricted, or a usage annotation as unrestricted if we can split it into itself. Let's now have a look at some of the typing rules. For example, the typing rule for the first projection, we require the value we are projecting to be a product type, and since we are discarding the part that we are not projecting, we require it to be unrestricted. When we terminate the process, we want to make sure that whatever is left is unrestricted as well. When we are receiving on a channel, we first need to split up resources, dedicate some of them to selecting the channel that we are receiving on, and some of them for the continuation process. The channel that we are receiving on will have to be a channel, and it will have to, we will consume one input annotation and 0 output annotations. In the continuation process, we will then have the type of the payload, the type of the payload of the channel available as well. When we are sending something, we will have to split twice, and that is because we need 3 things. We need first the channel we are sending over, we need the thing that we are sending over the channel, and then the continuation process. So here, as you can see, the payload of the channel and the thing that we are sending over the channel have to have the same type, and we will consume 0 input annotations and 1 output annotations on that channel. Remarks on what I just introduced. As you may have noticed, you can use omega to lose precision at any point. So when you're adding up 0 and 1, you can either say 1, or you can also say omega, and that's perfectly fine. So you can lose precision. And that is what allows us to say that receiving and sending require usage annotations 1, 0, and 0 and 1, because the channel that we require to be typed in this way will occur after a context split has taken place. So the context split is what allows you to actually go from, for example, a channel that has usage annotations 1 and 0 to one that has, for example, omega and omega. Another thing to note similarly is that when we, for example, do the first projection and we require one of the sides to be unrestricted, these expressions always occur inside processes after context splits have taken place. So again, it is here that you can not lose any generality and make fully linear products typable. Okay, so now that we have introduced our type system, let's see what the problem is with doing typing inference for this type system. And let's do that by having a look at an example. Here we send twice and then we terminate. We first send a unit as a payload over channel A, and then we send channel A away over channel X and terminate. So A is going to be used once for sending, and X is going to be used once for sending as well. The payload of X will be whatever the type of A is at that point after A has been used once for sending a unit. And then when we terminate the process, we require that both A and X are unrestricted. So in this example, this process will be well typed under the following typing assignment, and this is for any M. A will have to be of a channel type, since we are using it for sending something over it. And it will have to have multiplicity 1 as output, but it can have any multiplicity M as the input usage annotation. For channel X will have to have input usage annotation 0 and output usage annotation 1, since we are using it for sending, and the type of the payload will be the type of A at that point. So A will have consumed 1 for sending, so it will have the payload type will be a channel of input usage annotation M and output usage annotation 0. So this again is valid for any usage annotation M, and although this process is well typable, it is under constraint. It is polymorphic on some of the usage annotations. At how we could go about doing inference for this type system, we won't only have equality constraints, we will also have splitting constraints, and satisfying these means finding a substitution that you can apply to all 3 elements in the split, such that when substituted you can add them up as per the context splits defined before. So as we saw in this type system, you can have usage polymorphism, and so you can have under constraint problems. So you could have a constraint system where you have a constraint X to be split into 1 and Z, and no other constraint on Z, so that would be polymorphic on Z. This means that we cannot always solve these constraints eagerly as we create them, which means that we'll have to keep them around to be solved later. So we'll have to pass them through the inference algorithm. When we do that, the types of the inference algorithm are slightly different. So we don't infer maybe a context anymore. What we do is we infer for some kind and context of metavariables, we infer a context and a set of constraints on those metavariables. Here we represent untypable processes by constraints that cannot be satisfied, so we drop the maybe. In the case of expressions, as before, we will also return a type. When we follow this route of delaying constraint solving for later, we need to restate our meta theory, soundness and completeness, so that they take into account this deferral. So for example, for soundness, we say, well, if we infer some typing context gamma and some set of constraints C, then for whatever substitution that satisfies these constraints, applying that substitution to the context will make the process well typed. So here we don't return we don't apply one particular set of substitutions. We say any set of substitutions that satisfies the constraints will do. Similarly, for completeness, if we infer the typing context of B being gamma and C, then we say that for whatever typing context that makes B well typed, then we will find a set of substitutions that will solve the constraints that we created, and furthermore, this set of substitutions will be the exact specialization you need to go from the typing context that we inferred to the typing context that you have given us. So to summarize what we just saw, we presented a typing inference algorithm for the linear pair calculus. As we saw, usage polymorphism means that we cannot always eagerly substitute constraints, that we cannot solve them in place, and so we need to defer that to later, potentially leave it for when the process is completely closed, and then we can choose any solution. And that means that we need to restate our meta theory to take into account this possible delayed constraint solving. I'll be resuming work on this project in November, and we have several ideas. One is to, instead of keeping a set of constraints, to keep a tree of constraints that follows the syntax of processes and expressions. This way it's easier to know how things depend on each other and where they come from, making potentially the solving of constraints easier as well. Another idea is to actually implement eager constraint solving instead of deferred constraint solving, making the meta theory a lot simpler as well. And to do this, we observed that splitting constraints always take this shape where you have a constant on one side and potentially a meta variable on the other. So it's always the case that for each usage annotation is polymorphic in at most one position. So this means that we could potentially translate the types into tuples where you have a constant on one hand and a meta variable on the other. So in the example below, where we split x into y and z, we could eagerly solve that into a substitution from x into 1 and z. But we haven't thought too much down this road, so another possibility would be to maybe generalize this problem for the case where you have more than usage polymorphism on more than one usage annotation at the same time. And other than that, we have to, of course, whatever we choose to do to finish proving the meta theory. So thank you very much for your attention, and I'll take any questions or suggestions you might have.